So, next on the topic, I should say before I go on with the lecture, I've changed the syllabus a little bit. Okay, it's updated. As I mentioned, I did decision trees. That was just a classification or regression method that has been used for a long, long time. Really, really popular, a simple one. I took that as an example of showing you that, for a task, classification regression task, there are many ways to classify or performing that task. There's Gini, there's entropy, information theoretic method. There are various ways to do it. You can grow the trees, deep, really, really deep. There are various parameters, and there are many. Each of them would give you a different performance. I took that as an example of just introducing machine learning. And instead of continuing on with classification and regression, which is a supervised method, I have decided to start with unsupervised learning. Okay, so unsupervised learning is data without labels, and we looked at clustering. Next, we're going to look at dimension reduction. And one really, really popular method that's used a lot is principal component analysis, PCA. And that's what I'm going to be talking about. And then I'm going to be talking about density estimation. So that's how we are going. I've also released the project outline. So I talked about that last class. Homework will be out probably tonight, okay? Which will involve 4 or 5 problems, okay? Which is, it can be quite long, and I would suggest that you start a little bit early, okay? And the homework will cover probably lectures, next week's lecture. But some of the problems would be covering materials that we've already covered. Oh, and also, in order to have more student participation, what I'm going to do, or the TAs have suggested this, questions that I've asked for students who participated will get extra credit, and the TAs will note your student ID number and will give credits, okay, at the end of the semester. So that's to encourage you to participate in class discussion. Okay. Any questions? Okay, and someone asked me, is this machine learning? Yeah, many of the techniques that I'm discussing in this class are machine learning techniques. It's pattern recognition techniques. It's quite old. It's not really recent, but it's technique. It's basic technique that you need to know in order to understand advanced machine learning techniques. Okay. So it's unsupervised learning, and the technique that I want to discuss is principal component analysis. Okay, method for performing dimension reduction. Okay? And it finds a linear space spanned by a small number of orthogonal vectors in a new coordinate system. It's a linear transformation of the data that you have. Okay? So you have, if you have an n-dimensional may mean, you know, it could be 1,000, it could be 1,000,000, and you want to reduce that dimension to something reasonably small, and that maybe, you know, 1,000,000 into something like a 300-dimensional vector. Okay, and that 300-dimensional vector should contain all the information, or a lot of information that a 1,000,000-dimensional data has. Okay, for performing your task. Okay, so it's finding a new coordinate system. Okay, and these coordinate system is called the principal component, and the coordinate is it's an orthogonal. It's defined by orthogonal axis in the direction of maximum variability, and this will become more apparent. And you would want to project your data onto this new coordinate system, which is a smaller dimension. Okay, and this coordinate system would capture maximum variability of the data. So there we go. So I've shown you this as an example. Here it is. Picture right here. Data is in a 3-dimensional space, and the data is distributed on this manifold. Data is lying in this manifold. Rather than working in this 3-dimensional space, if we can somehow, the word that's used, if we can reduce the dimension such that we're working in the 2-dimensional space, in fact, or unroll this Swiss roll, so unrolling this Swiss roll, this looks like a Swiss roll, and work on the 2-dimensional space, it will be more meaningful. Okay. Yes? Yes, I just wanted to say, because the Euclidean distance between, so a point here and a point here on this manifold is quite far. It looks like those 2 points are near, but you can see on this manifold it's quite far. Okay? But data that lies here and right next to it is probably closer. Okay? And we call this distance, by the way, geodesic distance. Geodesic distance. I don't know if I'm writing this. So on this space, Euclidean space, point here and point here, the distance, the Euclidean distance is more meaningful, right? They're right next to each other. Here, they're right next to each other, but really they are really far on the manifold. Any questions to this? Yes.
When we do this unrolling, wouldn't be some information like be lost?
Pardon?
Wouldn't be some information lost?
Information be
Lost. Like
so
because we going from 3 dimensions, for example, to 2 dimensions, and is it like let's say like I think that some information.
okay.
would be
So in when you do dimension reduction, there are dimension reductions where you lose information. But as you see in this case, there's no loss of information in this case. But in general, you're right. You lose information. And in PCA, you generally lose a little bit of information. Okay? But the important thing is I have some task. Okay? I'm trying to perform a certain task, and maybe the gain that you get by dimension reduction may be more than the loss that you incur by doing the dimension reduction. Okay? So you have to think about trade-off. So here are some other examples. So in this case, data lies here. And you can see that all the data have the same X3 value. Okay? And you may have, this is sort of the extreme. Let's say there's some noise on this side, up and down. But let's say X3 value is pretty much the same. It will be better to work on this dimension. So there's another example here where the data lie on the plane, on this plane. But it's, the data points are lying in the three-dimensional space. So it will be best to work on this plane, two-dimensional plane, rather than this three-dimensional. So the need for dimension reduction. This is a very important area in machine learning. Okay. The world, we live in a world of high-dimensional data. Video, image, that's high dimension. Okay, you can think of each pixel as so the image is composed of pixels. So it's x1, x2, x3, x4, and so forth. And you can write this thing as a vector. It's high-dimensional data. Okay. And you can see, you would imagine that the data is highly correlated, meaning that this value and this value are very close to each other. So there's probably some low-dimensional space. So image, when you take a brain scan, okay, MEG, it's magnetic, EG, and that's huge. Genomic data, it's huge. I mentioned this document. Okay, a document is composed of many, many words. Each word can be represented by 70,000 vector, because it's a word. In the word, there are about 70,000 words, English word in the dictionary, and it's one of the words. So it's a 70,000 dimensional vector, each word, and there are many words, so it's huge. Okay. And the idea of dimension reduction is some features, so some of these values are irrelevant, and these features act as noise when you're performing a certain task. Okay, they don't provide relevant information. I just would like to say, speech. I'm talking to you, and my voice contains many information. For instance, not only the message, but also my age, also my mood, my gender. Various information is contained in my voice. Okay? When you talk with someone, you sort of get the feel what this person is going to be. Right? It contains a lot of information other than your message. But let's say my task is to do speaker recognition. Okay, who this person is. Okay? Some of these information may be irrelevant. I'm doing speech recognition. If I want to do speech recognition, it's irrelevant what my gender is. It's irrelevant how old I am. All that information is contained in my speech, but there's lots of information, but only some of them are relevant for performing that task. Okay? That's another example. Okay? So some of the features act as noise, and you want to extract out important information from this high-dimensional data that would be relevant or helpful in performing your task. And another thing is, when the dimension of the data is high dimension, okay, it's very difficult to visualize. Okay? We can usually visualize up to 3 dimensions. But if you go million, how do you visualize that? Okay? So you want to go into low dimension and visualize how the data are distributed. So that's another reason for doing dimension reduction. Okay? So, and also this intrinsic dimensionality may be smaller than the number of features. So even though dimension is huge, maybe there are only few small dimensional data that's controlling this high dimensional data. And another reason for doing this is hard to store this high dimensional data. A lot of storage space. So you want to reduce the dimension. And there are many dimension reduction algorithms. Okay. More advanced algorithms, but we're only going to cover PCA. Okay. It's a simple algorithm, and it's the most popular algorithm. Okay. And someone asked me, came to me, is this machine learning? Yes. But there are lots and lots of different dimension reduction, more advanced dimension reduction. But it will be stupid for me to talk about some advanced algorithm without introducing PCA. So, let me start. I'm going to start with PCA. Okay. So let's say I have data that is D dimension. Okay. And I have lots of data, and the nth data, there are n is going from 1 through n. N is huge, and D is the dimension. I could, what I'm trying to do is I'm going to represent each dimension. I'm going to take a linear combination of the elements. So here is I going from 1 through D. Linear combination of the elements of the data. I'm taking a linear combination. I'm going to add a bias to transform that data to another data, Z, okay? And I'm gonna do this for Z 1 through K. Okay, so I have a d-dimensional data. I take some linear combination, add bias, and convert it. And I have K of them. Okay. And how do I represent this by a matrix? I can represent this by a matrix. Zn 1 through Zn K, represented by a matrix and X and 1 X and oops. Plus U01, U0. This would be U, U1 through U, let's say, K, UD. So there's I'm taking this n d-dimensional data, matrix, multiply, add a bias. It's a linear transformation. And when I'm doing dimension reduction, what I have, K is usually much smaller, I should say, is smaller than T. K is less than T, but in general, K is much smaller than T. Okay? So this is the theory behind PCA. I want to do some linear transformation of the input data such that I have a lower dimensional data. Okay. So this is K by D. Now, so PCA is linear transformation. Now I have showing you on the left-hand side some data, the x's, the original x's. Here, here it is, here it is, here it is, here it is. It's two-dimensional. And I'm going to project that data onto a line. This is case one, and this is case two. Now, by the way, I just want to also say that it's linear transformation, and also you can think of this as projection. I'm projecting this point onto the column space of this vector, or of this matrix. It's projection. Okay, transformation, projection, and then you add a bias. Okay. Everyone understand projection? And as I said in the beginning of this course, a prerequisite of this course is linear algebra. Okay, and I hope everyone has. So I'm projecting these points on the left, either in case one, onto this line. Another projection, case two, just projecting it onto that line. Okay? The two cases, case one and case two. And my question is, which projection would you prefer?
The second one, because you want to minimize the information loss.
Okay, that you could say that, or another way of saying. So, as you're projecting, let's look at this case. As you're projecting onto this line, you are sort of removing this information. All this information. How far are you from this line? All that information is lost as you're projecting. Okay? And in this case, you're losing all this information. How far are you with them? And you can see that as you're comparing 1 to 2, you have a smaller loss. Okay? But what I want to get at is not the concept of loss of information, but variability. Okay? As you project on this line, so the points are here, the points tend to be what? Squashed together. Whereas in this case, the points are spread apart. So the variability here of the projected points are greater on this side than this. And if you want to retain the information as much as possible, the difference in data points, the information that's contained, you have more information retained in this than in here. Okay. So, rather than the concept of loss information, you want to maximize the variability. Okay, we want to look at projection, linear projection. Okay, so how would you get this point right here? Let's say I knew this. How would you get that point? And it's going through the line. How do you do that? Pardon?
Inverse of matrix supposed to use from Z to Z. That's not so
Let's say I knew let's talk about it in terms of vector. Okay? It's easier to talk about in vector. So the vector here, you take the inner dot product. Well, inner dot product, I hope everyone understands what inner dot product is. If you take the inner dot product, it gives you the distance. You're going to be on this axis, right? And the difference between all these points are the distance from the origin, right? So and you take the inner dot product, and that will tell you how far you are from the origin. Okay, that's simple enough. So the notion of, yes?
Is there any concerns on like threshold of loss? For example, if you have 5-dimensional data, like whether we would choose
What?
to move,
If you have,
if you have 5-dimensional data,
yeah.
if you would choose to move to 4-dimensional or 3-dimensional data, do you have any threshold of loss or how many percentage or something?
That would depend on your task, and the performance that may be required. Okay. So I'm going to project it So I'm starting with 100 dimension, D is 100, and my performance requires me to do something in my storage space and so forth. That will determine what K should be. Right?
So what will be the index of loss?
Pardon?
What will show your error? How much information was? So it is just simple distance.
So the loss will be, as I said, these will be all loss, square loss, okay? And how do you measure loss? Square distance, okay? So, yeah. So the loss will be determined by this. From this coordinate system, so if you project it, you want to reconstruct this information, right? How far are you? So how far, so this is the reconstructed point, right, on this two-dimensional space. The data that you'll be working on, okay, so let me just say this thing, x1, x2, and so forth. Let's say this is x1, x2, so it's two-dimension. x1, x2, these are all two-dimension. They will be converted into that distance, r1 and r2. r1, r2, and so forth. Right? r1 and r2. That will be your new feature points, right? These are two-dimension, right? But we know that R1 in two-dimension is this point right here. That is X1. That's the reconstructed point. That's the reconstructed. So from here, we could get all these points. That's the reconstructed point, right? From this, we can get all the green points. Huh? And the error will be that. And that will be the arrow. Okay, arrow. You understand what I'm saying? Right here? Okay, so the notion of variability, or I should also say that you want to find a projection where the variance is large, where the variance, the projected variance is large. Okay. This is going from two-dimension to one-dimension. But we can think of five-dimension going to three-dimension, five-dimension going to two-dimension, million-dimension going to 300-dimension. So the basic algorithm for performing TCA is this. You're given n number of d-dimensional data. Okay, and I'm assuming that D is big, and it's represented by a matrix X of size D by N. So it looks like this. X1, And each one, right here, is d dimension. And how many? I have n dimension. And that's x. Okay? So I have stored all my data into a matrix. So this is what I'm starting out with. And the first step, so it's a 5-step process. And the first step, you subtract out the mean. Okay? You subtract out the mean, so the mean, you take the average here, take the average there, and then you subtract out. Okay? So essentially what this process is doing is taking this, all these points, and shifting so that it's centered around the 0, 0 coordinate. Okay? You're shifting all of that. So there are all, so the mean value of the data is 0. So we take xc. And then you compute the variance, the covariance of xc. What is a covariance? Who's heard this thing for the first time? Okay, I hope everyone knows what covariance is. Right? Okay. Covariance, just for the case, for those of you who don't know what covariance is. So I have data x1 through xd, and the covariance, the mean, often represented by mu, is the expected expected value of each of the dimensions. Okay? Now you may say, what? Maybe I'm making it more. It's just the average value of this dimension. Okay? This dimension can take on many values. Probabilistically, the average. Okay? The mean value. And I'm sometimes going to denote this like this. I'm going to do this. I'm going to somehow write it like this. Okay? Expected value of this vector. Covariance, often denoted with a sigma, a big sigma, is a matrix X. Let's say it's an the element ij. Let me just write this one rather than each of them. The ij element is x I minus ui. Since I haven't written ui. Transpose. J. ijth element. Okay? It's a matrix. What's the size of the matrix? It's a d by d. D by d, right? That's the covariance. Now, I've removed xc. What is the mean value of xc? It will be 0. Okay? What is the covariance? The estimated covariance? So all these values go 0, 0, and it will turn out that it's this. Okay? You're taking the outer, you take this matrix and then take the average, this will be the covariance. Okay. Estimated covariance. And the third step, I'm going to go through all of this. So it's a d by d. Then you take the you perform an eigen decomposition, eigenvector and eigenvalue. I'm going to go through the proof. What do you think the eigenvalue gives you? What do you think the eigenvalue gives you?
Scarce.
Pardon?
Scarce in shape.
Very good. It is the variance, yes, it's the variance in that dimension. Very good. Okay? And this is one of the projections. If you project it onto this, that gives you the variance. Okay. And so how many, if this is a d by d, how many eigenvectors and different eigenvalues would you get? D. Okay. And I should just tell you that the covariance matrix is full rank. Okay, it's full rank. Okay, and it's symmetric. Okay, covariance matrix. But I don't want to go through all of this because, and then it makes it. And what I'm going to do, I will get d eigenvectors, okay, d eigen projections, possible projections, but I'm going to choose only k of them with the largest eigenvalue, which is projections onto top k with highest variance, projected data variance, right? And then you project all the data, onto this new k eigenvectors, and then you've reduced it to k-dimensional data. So what do? You find your k eigenvectors, and you take the inner dot product. Eigenvectors d-dimensional, you got k d-dimensional vector. So for each data, you just take the inner dot product, and that will give you the new coordinate value for that vector. So I'm going to go through this. So here are some examples of PCA. So you can see that this data point, this purple line, a two-dimensional space, and sorry about this notation, and it's been projected project it onto this line, which is a one dimension, right? As you project it, it becomes a one-dimensional data. Here, you have a three-dimensional data, and you're going to project it onto these two lines. They are orthogonal. By the way, each of them are orthogonal. And you're converting it into a two-dimensional data. So this data is lying in a three-dimensional space. And you find so you subtract out the mean value, and then you find the covariance matrix of this data, and then you pick out two eigenvectors with the highest eigenvalues. And you'll find that the eigenvectors are orthogonal. This is a property of a symmetric matrix, full rank symmetric matrix. They are orthogonal. The eigenvectors, so this is the eigenvector, this is the eigenvector, they are orthogonal. And you're going to project each of these points onto these eigenvectors. And the projected value, projection is, the process of projection is taking the inner dot product. Projected value is the new low dimensional feature. Okay. So a little bit about covariance. Okay. You have this is a covariance matrix of this data. This is a covariance of this, and you can see that data that's spread out like this. By looking at this data, which is in a two-dimensional space, do you think there are some correlation between x1 and x2? So another way of saying this correlation, if I look at the value of x1 of any of these points, can I make some prediction about x2? No. Right? It's difficult because they are just spread, in a circle like this. And you can see that the covariance matrix is in a sort of a diagonal form. So this is, what does this value give you? It's two-dimensional, so the covariance matrix is what? Two-dimensional. What is the first element? What is the first element saying? Variance. If I project it onto x1, that's the sort of the variance, right? That's the variance if I project it on x2. What about these diagonal terms? This is the cross covariance value between x1 and x2, and you can see that they're very, very small in comparison with this value. Okay, so you can't say very much. So performing PCA on this, do you think it will be meaningful? No. You'll be losing a lot of information, right? What about this type of thing? You can see that there is strong correlation. If I know the value of x1, I can make a pretty good prediction on x2. X1 tells me something about x2, so which means there's strong correlation between these two components. And you can look at, if you look at the covariance, the off-diagonal term is very high. Okay. covariance is defined this way. Covariance, in the truest term, requires knowledge of what? What do you think this P is? I didn't have P in my other. Yeah, probability. Okay? The joint probability of x1 and x2. Right? But we don't have this. Okay? In order to take, so this is the this is the same as taking the expectation of this. Right? I hope everyone says. Probability is also sort of a prerequisite for this course. I just want to mention this. Because some people say, oh, this is an introduction to machine learning. This seems more advanced. I'm assuming that you understand the concept of covariance. Okay, many of the probabilities. Okay, this is the expected value. Okay, so I'm going to go. I'm going to define sample because I don't know this, the joint probability of the data, okay, of x1 and x2 value. X1 is the coordinate in one of the dimensions, xj is the data in the other dimension. I don't know the joint probability. So what do? I consider sample covariance. Okay? From the data, I can make a sort of an estimation. And this is the sample covariance. Okay? It's taking, you subtract out the mean, okay, of the sorry about this, is the ith data, and this is, this should be, yeah, it should be j. Okay. Oh, no, this is the same data. This is a vector, by the way. Okay, it's a vector, right? And I subtract out the mean, right? So this is a two-dimensional, and this is two-dimensional, and I take the outer dot product of all the data, and I take the average, not by dividing by n minus 1. This is sort of an unbiased estimate. This is the mean, and this is what n minus 1. Okay? Okay, so it's also, I'm thinking in PCA, I'm thinking about k orthogonal vectors of dimension d. Okay? So these are the new coordinate system. K of them. I've shown you one examples with one of them. I've shown you with U1 and U2. So it's just two. This is U2 and this will be U1. This will be U1. K. So this is sort of a vector. I'm going to define matrix A that places these coordinate vectors. K of them. So this A is a K by D matrix. And I'm going to project my ith data onto this new coordinate system to get yi. Okay? So yi is a vector of k dimension, where each element is the value of, in this UI axis. Okay, that's how it goes. And I'm going to assume that the xi is zero mean, without loss of generality. How do I, if the data is doesn't satisfy this, what do I do? Just subtract out the mean value. Right? I get that. That's no problem. What is the covariance value of yi? What is the covariance value of yi? Which is this. It becomes that. It's A transpose N A. You can work this out. Okay? And what I would like in PCA, or this is another way of saying taking the performing eigen decomposition, is to make this thing into what? A diagonal matrix. Okay? This is like taking the covariance of this and performing eigen decomposition, or getting the eigenvector and eigenvalue. Okay? So, what is the objective in PCA? So we know that PCA is finding a new coordinate system such that you get maximum variability, right, in each of the coordinate system, right, or each component axis. So what is PCA about? What do you want to find? You want to find these U's. What is U that will give me that this is some diagonal? Okay? That is PCA. So this is just represented in this another way. This is the data matrix. Okay, the data, d-dimensional data are column vectors, and I've put them in this matrix. And I want to reduce it to k by n. Okay? Reduce the dimension. Done. So what am I doing? Each of this data is represented by taking a linear combination. So I have a new coordinate system, which is what's the dimension of this? UI? What's the dimension of each of the axes? I have k number of them, but each one is d-dimension. Right? This is d-dimension. I want to take a linear combination of that to reconstruct the original. Zn, how would I get Zn? How is Zn obtained? How would you get Zn? Linear combination. That's what it says. How would I get Zn? We also know you also have to understand that UIs are what? The UIs, there are k number of them. The UIs are what? U basis, but they are orthogonal. Orthogonal. So how do I get the Z? I just take the inner dot product with each one of them. That's how z's are. Okay, now it will turn out. Actually, there is something wrong here. Can someone tell me what's wrong with here? This equation right here? What's the dimension of this? D dimension. This is D dimension. What about the dimension of that? What? 1. It's a value, it's a scalar value. What does this mean? It means this is the nth data. Nth. Okay? Nth data. D dimension. This is the ith coordinate. Ith coordinate. How many do I have? K number of them. That is just the scalar value. How many do I have? How many do I need? Oh, K number of them. Oh, so here, in order to get, okay, so this is correct actually. What will be the reconstructed? How would I represent that? And I'm going to use PCA, not D. Okay. Right? So if I use all D, then I can get the exact reconstruction. Exact reconstruction. But if I use K, I'm going to be off by a little. Everyone understand that? So, I also want to somehow minimize the difference between that and this. And minimize that. So there are a lot going on. I want this coordinate system to be orthogonal. Okay, I also want maximum variability on the projections, K number of them. I also want to minimize the error, the reconstruct. So this is reconstructed using only K. This is the original, and I want to minimize this. Okay, that's what this should be doing. Okay. That's what it should be doing. Okay. How do I find that U? So U1 through UD is called the principal component. What does this mean right here? The ith component and the jth component, if I take the inner dot product, they'll be orthogonal. Only when I and j are the same. Then the value is what? Yes. So let me just define delta ij. Delta ij is 1 when I and j are equal, is 0 otherwise.
Can I ask one question?
Yes.
So I understood this new principal axis, like U1 to UD or UK for example.
Yeah. So
And
the
this is-
so UD from this, if I use all D dimension and I'm saying, then I get perfect reconstruction. There's no loss of information, right?
And the eigenvectors that we found from this covariant matrix, and I mean, eigenvectors, they are like not necessarily be unit vectors. Did we convert it by the like to the?
So let me just go through this, okay?
Ah,
Okay, let me just go through this, okay?
because I think that
Yeah.
the y is one, not like absolute value of.
Okay, let's go through this. Okay, those are good things to think about. Okay, so I hope everyone's understands. So the coordinates are orthogonal. Okay, we want orthogonal. Well, orthogonal we sort of get automatically by doing eigendecomposition of a symmetric matrix. Covariance is a symmetric matrix. Okay, and it's full rank. This is, I'm going to assume that without loss of generality that it is centered on the origin. And I could do that by subtracting out the mean. Okay? So, if I project it onto this new coordinate system, that's that, right? So this will give me what? So yes, that's the distance on each of the coordinate, new coordinate, right? And then I take the average, squared and the average. Okay, so that's like the covariance. Okay, that could be represented by that way, like that. Okay, so U is a vector. U is a vector. Okay, and then I take sort of like the inner dot product. That's the variance, right? Variance. Variance. Oh, not the variance, but square value. It's zero mean. And then I take the average. And I do that for all the data. That's the variance of the projected onto U. So I have one axis, U. I take the inner dot product, right? And I square it, and I take the average. This is the variance onto that projection data. And I can represent this in a matrix form that looks like that. Okay, everyone understand this? Now, my objective is this. I want to maximize this. I'm going to be using this type of notation quite often. Maximize the projected variance with respect to U. Okay? With respect to U. Such that, what is that? The projection is what? Is unit value. Okay? You talked about this. Orthonormality, but this is unit variable. So how do you do this? You take the Lagrangian. Okay? So you say, oh my goodness. So you want to maximize this. So this statement above here, this statement is the same as maximizing this statement here. Okay? This value minus lambda U. Okay? And I'm going to explain why this is so. Okay? So how do I maximize from this is constraint optimization. Constraint optimization, maximizing some value, right? Constraint optimization, taking the Lagrangian, and I'm going to explain why you want to do this. How do you do this? How do you maximize this with respect to U? So look at this. What kind of a function is this? What kind of function would this be? In terms of U. It's quadratic. Quadratic means only the elements, there's the highest order is a square. There's a global quadratic function. There's a global maximum minimum. So how do I maximize this? Take the derivative. Okay? And by the way, this lambda is called the Lagrange multiplier. Okay? I'm going to be talking about this a little bit. And set it equal to 0. So if I take the derivative, if I take the derivative of this, what do I get? There's some typo again here. If I take the derivative of this, it equals that. And set it equal to 0. Okay? Can we fix this? Okay? If I take the derivative of U transpose X, X transpose U, minus lambda U transpose U, and set it equal to 0, I get that. Okay? Okay? At least for that. And if I rearrange this term, I get that. So what is this? This is eigenvalue decomposition. U is what? U is what? The eigenvector. Lambda will be what? Eigenvalue. Okay? Now, because this is a symmetric matrix, what are the U's? If I found different values of U, this is a D by D. So how many, and it's full rank, how many distinct eigenvalues would I get? D number of them. Okay? D number of distinct eigenvalues, eigenvectors, because it's full rank. They are, this matrix is also symmetric. So from some symmetry, you get that the eigenvectors are orthogonal. Okay? So I got normal. So it's, because it has to satisfy, this is orthonormal now. Orthonormal because of this. Okay? Now let me just go through this a little bit. Okay, so so essentially, PCA is performing eigenvalue decomposition on the sample covariance matrix. It comes down to that. Okay, that's what I want to say. Okay, 15. Oh, I gotta go. Okay, so what do I do? Usually, I look at the eigenvalues and I sort of threshold. If the eigenvalues are less than, let's say in this example, 5, I throw all of them away and keep the one with the highest one. And here, so this data, which is 10th dimension, is, if I threshold it by 5, what's the dimension? 4. Okay? Eigenvalue decomposition. Let me just explain this. Actually, I won't have time. It's 10:16. So I stop right here, and I'll continue on next time. Okay? To talk about a little bit about Lagrange multiplier, because people may not be familiar with this. And we're going to be using a lot of Lagrangian